So what we'll do this morning is a lightweight introduction to where we are with PQC. And then later you'll hear the experts about their open source libraries. Who here knows a lot about PQC? Not that many. Okay, so it's a very high-level introduction, not make it too challenging. I first tell you something about cryptography to understand where we are. Then we look at the quantum threat. We look at PQC then, at high level, what it is. There is no mathematics in this talk. There is only one equation, which you will all be able to handle before noon. Then I'll talk more about the policy issues. So until about 100 years ago, cryptography was only used by kings, generals, and diplomats. And then something changed, which is wireless communication. So now also businessmen started to send messages, but also it became much more important because now admirals could talk to their fleet in real time over wireless communication. Then actually we had the first crypto boom, and Hagelin started building his first machines, purely mechanical machines. And then, of course, as you all know, as things heated up, electromechanical machines were built like Enigma. So they used a combination of mechanical and electronics. And also, but it's interesting that in fact, already in the 20s, people were using this for commerce, for buying shares and making business deals. Wireless communication was used. Then things turned into electronics, got integrated, and the first application beyond government and military was finance world. So the banks started using cryptography in their mainframes with cryptographic devices, all in hardware. And then 50 years ago, Diffie and Hellman invented public key cryptography, which actually made it possible to use cryptography at a large scale because they realized that, in fact, to have a private conversation over an open network, you don't need to have agreed on a prior key. This is what we use today if you talk to Amazon or Coolblue or Google or your favorite social network. In fact, public key cryptography is used to secure communication. They also made another invention. They invented signatures, legal signatures, which are used today for authenticating users for code updates. And this is widely used. But interestingly, Diffie and Hellman did not invent a scheme for encryption or not a scheme for signatures. They only invented a scheme for key agreement, which actually is still very important today, is the core of TLS and SSH. But Rivest-Schmier and Edelman invented then a solution for the problems, public key encryption and signatures. But maybe it's hard to realize now, but in fact, people couldn't implement this stuff. There is a very interesting series of papers by the famous Turing Award winner Ron Rivest, and in the 80s, he tried to build an RSA chip, and he never succeeded, because he actually had to make new tools to build RSA chips, because the hardware tools were not powerful enough to make RSA chips. So the first RSA was only used in the late 80s in hardware. And so there was some cryptography in GSM late 80s, and the financial world started also using encrypting more. Then a very big change happened again, software. So cryptography became adjusted to software. Computers became fast enough, so you could now do cryptography in software. And that meant also that governments could control it, couldn't control it anymore. It became actually much more used. So the first big use in the 90s was, of course, TLS or SSL, it was called at the time. GSM, where actually the key derivation happens in software in the SIM card, and encryption happens in hardware in the phone still. And then EMV happened. This is credit card payment systems, public key cryptography in a smart card, actually with algorithms invented in Belgium. So there was large-scale adoption. It was only something of tens of millions. But then Snowden happened, and then we got to billions, more or less. Then we really got rollout of TLS. So in even 2012, there were only like 10 million servers with an offering TLS, and most of them had an insecure certificate chain, half of them. So in fact, there was only a couple of million servers that actually were giving communications, although TLS was invented in the early 90s. 20 years later, the usage was still quite limited. Then Snowden happened, and then people started having end-to-end messaging. And TLS, now there is 600 million servers offering TLS, and there is 10 billion devices or 15 billion or 20 billion talking to those servers. So it's now really mass adopted, and now we get problems with law enforcement, but that's a different story. That's not for today. And of course, the next big thing is PQC. So this is more or less cryptography in a nutshell. So The total number of cryptography deployments, and here I count every library, every application, every card you may have, is probably close to 100 billion now. It's not all on the internet, right? I mean, for example, my access card here, this is not on the internet, not an IoT device. About 60 billion of those is public key cryptography. So it's an amazing success because it could not be built in the 70s and 80s. It was millions or tens of millions in the 90s, and now it's 60 billion. So what are the big applications? IoT devices. Try to buy today a dishwasher or a dryer without an app and without connection to the manufacturer. You will not be able to do it. And if you switch it off, you will not get all the functions. So you're now more or less forced to put every device in your house on the internet. Then very big, of course, also is EMV, so the credit card payment system. Something like 100 million terminals and 5 billion cards, all public key cryptography based. The update system on your phones and all your devices is public key cryptography based. Then WhatsApp, all the messaging, WhatsApp, iMessage, Signal, Telegram, and so on. Again, billions of users. Content protection, the Netflixes and the likes. Then there is still also local banking cards. There is the gaming industry. By the way, a statistic I really like is that the turnover of the gaming industry is larger than the cybersecurity industry. So be aware of this if you want to understand what is important in this world. Okay. So cybersecurity industry is 250 billion. Gaming industry is more. And then we have the passport and identity cards, all the terminals and so on. So this is how I end up in more than 60 billion. But migrating things takes a long time. I can tell you an EMV story. EMV was rolled out in the late 90s. And in 2008, after 10 years, they decided they would move to elliptic curve cryptography because the keys are shorter. And they made a migration plan. And they plan to complete the migration by 2028. So they discussed for 4 years in 2012, then they made the first standards. 2016, they decided that they would abandon it. Okay, and now they changed their mind, they're going to do it anyway. But so this is something that is very hard to understand in internet timescales, where ChatGPT goes from 0 to 1 billion users in less than a year. And changing the credit card payment system is a 20-year project. Okay, of course, they may be made obsolete, and we all may be with our phones, but that's a different story. But this is how things work. This is also a very nice graph made by Gaëtan Laurent based on data from SSL Pulse. This shows you how the versions of TLS evolve. So typically, versions of TLS are created because people find flaws. And so after Snowden, it was decided to really fix all the bugs and have really a secure version. But so more or less what you see is the adoption for a new version is about 10 years. And getting rid of an old version like SSL version 3.0, only because somebody created a poodle attack, but people started really getting rid of it. And then it's still not down to 0. So this is very important to understand. And this is the top 150,000 websites. Okay, there is 600 million. So this is the fast ones. So migration of cryptography is a pain. You have a GSM, if you have a phone there, it still offers GSM. It still has an algorithm from 1988. It's still in there, and it's still in there in billions of phones. And it's very hard to get rid of it. So this is something we should remember. And this is hardware, because the encryption in your phone is in hardware, but this is software. So I think it's a very important lesson. And why it's interesting, because actually cryptography ended up to be in software. And before, cryptography was in hardware. So in hardware, you put an algorithm in, and like in GSM, and then you put a second algorithm in for export outside Europe, which is, so GSM was kind of insecure, secure enough for you and me, but the police could break it. And then there is something which is even crappier, and this is for the rest outside Europe, like Australia, New Zealand, Japan, Korea. If they use GSM, they got really crappy stuff. But that was the option. So you have, in GSM, you had no encryption, really crappy encryption, or crappy encryption. And now there is OK encryption with a 64-bit key, which is still really bad. But this is hardware. So when TLS came, or SSL came, the idea was we're going to negotiate the algorithms. And so because it's software anyway, you can have 245 suites like there were in TLS 1.2. So in fact, you can have many choices. So the idea is that this problem of changing cryptography will be easy because we have everything in software and just negotiate. Well, it turned out we failed because TLS, the default algorithms are supported and all the rest breaks stuff. So more or less, even if we design for agility, we seem to have failed. And so we'll probably have to figure out how to fix this. In the early 80s, Feynman and also a Russian guy, Manin, had the idea of building computers that would be based on the principles of quantum physics, where a bit could be in superposition, could be 0 and 1 at the same time. And they imagined you could do really cool stuff with this. And people in physics found this really cool because the main application they saw for it was predicting physics processes. Because if you want to solve quantum equations, Schrödinger equations, and so on, you need actually very powerful computers. And quantum computers would be actually very suitable for this. That was how they invented this. And of course, there would be spin-offs in designing new molecules, new materials, new medicine. But that's what they imagined. If we can build computers that work like physics, we can actually do calculations about physics. But that was, they didn't think about Peter Shor. Peter Shor actually found in 1994 that if you do a fast Fourier transform, I guess most of you are familiar with this. It's an algorithm used to turn time into frequency, which is used all the time. If you analyze systems or if you want to make modulation systems, this is the most widely used algorithm. It turns out that the quantum FFT can factor and can compute discrete log. And why is this bad? Because in fact, the public key systems of Diffie-Hellman and RSA are based on factoring and discrete log. And this is all we have. And this is what we widely use. If I say 60 billion, it's 59.999 are based on factoring and discrete log. And so Shor has this algorithm. So there was kind of panic. So cryptographers at that moment started looking at new cryptography that would not fall for a quantum computer. Then in 2001, at Stanford, the first factorization was done. 15 was factored. It turns out to be 5 times 3. It took 2 PhD students in Stanford. One of them was actually a student from Leuven, who's now a professor in Delft. But also a team at IBM to make such a computer. So they built years on this and programmed it for years to factor 15. We'll come back to this. We know today that they have not factored 15. They actually programmed the answer in their computer already. So they already cheated. That's what we know today. So cryptographers started getting worried in 94. So more and more people are working on this. For example, I had my first student on this topic already in 2003 starting. And so in 2006, I had a project called eCrypt, and some people in our team organized the first post-quantum cryptography conference in Leuven. So this is now 20 years ago. So as cryptographers, we try to think ahead. So we already did 10 years of research before there was a community consisting of 60 or 80 people. And then we started working on this topic. So this is showing we go ahead. Of course, today, people announce quantum computers with thousands of qubits. We'll come back to this, or more than 1,000 qubits. So the idea of Feynman and Manin would have, more or less, you have entanglement, which means that kind of this is very spooky thing. You create 2 particles, you move them at a distance, and an operation on one still affects the other, and superposition. So something can be in 0 and 1 at the same time. And so they figured out that you could do really powerful stuff with this. Okay. So to give you an idea, Snowden leaked that even 12 years ago, the NSA already had spent $85 million on a quantum computer. This is like 12 years ago. So now probably you can add at least 1 0 to this, and maybe a small constant in advance as well. Why? Because they want to break stuff. McKinsey wrote a report a year and a half ago saying that China spent 14 billion on quantum technologies, but then later they walked it back to 4 billion. I guess you can make this kind of sense. Nobody can check this anyway. But at least it's now $1 billion industry. So as I said, Shor affects factoring and discrete log. And then if you look at RSA 2048, which is, for example, the default algorithm in the Belgian identity card, it was widely used by CAs for a very long time. Also for TLS, it was widely used. This was what typically people thought was the standard. And there was a paper by Google saying that you need about 4,096 qubits for this. There is many improvements where you need fewer qubits, but then more of this and that. And there is many quantum computers, we don't even know how they will look like, depending on the physics, depending on the architecture. So you can make trade-offs, but nobody really understands what the trade-offs are. But so more or less, this gives you an order of magnitude, you need about 4,000 qubits to break RC 2048. And the estimate was that it would need about 20 million real qubits, because these 4096 qubits, they have to be noise-free. And it turns out that the qubits we can build are not noise-free. So you have to do error correction. So more or less 19 point something million qubits are used for error correction and only 4,000 for computation. And then there was kind of a big shock, because last May, research of Google, who made the original calculation, actually showed that it's less than 1 million. So there is actually improvements in error correction that show that it's only 1 million qubits to get 4096 reliable qubits. There is also something called Grover's algorithm that says that if you want to search a space, like if you want to find something about a person in this room, it's actually enough to look only at one column of people. It sounds completely counterintuitive, but it's possible. With computers, you can do this stuff. And so the conclusion was that, well, you have to use, instead of 128-bit keys, 256-bit keys. And then this problem is solved. It turns out that if you look at the details, this is not true. This algorithm is not parallelizable. It requires for AES 128 2 to the 70-something gates. 2 to the 70-something gates, right? I mean, the biggest chips today have 100 billion transistors. This is 2 to the 34, okay? So 2 to the 70 gates is like, no, it's not gonna happen. Not now, not in 10 years, not in 20 years, not in 30 years. In 100 years, we don't know, but at least we can forget about Grover. But of course, people said, well, we have to upgrade AES 128 to AES 56. It's easy to do because the standard is there and everybody does it. It's actually not needed, but we do it anyway. That's what people do. It gives a good feeling, but there is no scientific reason. If you want to hear a long talk explaining this, there is a talk by Sam Jacques at CHES 2024 where he explains to you in an hour why you should not implement AES 256. But it gives you a good feeling. So why not? And it doesn't cost, it's 40% slower. So more or less Moore's law makes computers 50% faster anyway in a year's time, so you don't care about it. So some people also believe that computers can solve everything. No. In fact, what they can do here is the polynomial hierarchy, where you have the easy problems, polynomial problems, the hard problems, NP problems, where in fact it's easy to check an answer once you have it, but it's hard to, we believe it's hard to find it. And then there is those problems NP complete, which are, if those are hard, all the problems in NP are hard, right? This is the really hard problems in NP. And then there is the p-space problems. So what you can do in quantum computers is only a set that's slightly bigger than p problems. So people always think that computers can solve anything. No. Factoring, discrete log, Schrödinger equations, there's a few things, but in fact, we only have a very small set of algorithms for a very small set of problems. And there is some surprising things like this. Search is surprising, but it's not that, you know, every problem you want to solve will be solvable. This is what kind of the marketing wants you to believe. That's not the case at all. But of course, physics, chemistry, molecules, medicine, materials, there is an enormous potential, right? I'm not saying the AI thing, I think it's a different, this is not clear at all that computation will help AI more because nobody knows how to put data in a quantum computer. So, and AI is about lots of data. So there we're much more skeptical, but of course, if you have a buzz or hype, quantum and AI, you put it together and you get really money from your funders for sure. It's called quantum AI, and voila, the money will flow in. This is a slide which I got from Leuven van der Sijpen, so this professor in Delft now. This is 25 years ago. So what is interesting here, you see the number of qubits and number of gates. And so what you also see is up top names, MIT, Cambridge, Stanford. So in fact, this is, people think that this is something what only happened 5 years ago or 10 years ago, because that's when they started reading the newspaper about this stuff. No, in fact, already in the 90s, there was a massive investment in research labs. The people didn't get farther than a few qubits. So here is this famous computer in Stanford that used a special molecule with 7 degrees of freedom, so they could make a 7-bit qubit, and then they factored 15, but we'll come back to that. So what is the change now today? Quantum computers get names, and we see big press releases. And why is this? Because now the big players have gotten in. They now don't spend millions anymore. They spend hundreds of millions. They buy complete university labs, like that's what Google bought a complete lab in UCSB in Santa Barbara. So there is really big money there. And of course, if you're head of a division that consumes or burns 100 million euro per year, you have to a few press releases every year to announce a breakthrough. If not, your CEO will cut your funding. So this is the reality. I predict you that every year in 2026, every month there will be a new breakthrough in quantum computing. There has to be, okay? There has to be. Otherwise, these people lose their funding. How will you do it if you're in their place? You make a breakthrough, you have to make one. And of course, now you give your computer a name, cool names, like Majorana. Microsoft has 8 qubits, Amazon has 9, Google has 100, and IBM and Atom, they have the most. But if you talk to the experts, the most powerful one actually is Google Willow at this moment, the one announced a few months ago, because it's not only about qubits, it's also about noise, and it's about time it stays stable. And more or less, all the others have lots of noise or are very short, can't do anything really useful. So in fact, and this may change. There is also, by the way, lots of startups. If you're in physics, and you have you can do some cool stuff with spin of electrons, and you can make a nice business plan. You can also easily get 50 million to actually say, I'm going to build a quantum computer, and you will find some gullible people that will give you money, and maybe you'll even succeed. But this is what's happening. It's a space with enormous dynamics, and the stakes are very high. The marketing capabilities will not be so high. I mean, the NSA may buy you, or the Chinese may offer you a lot of money, but I think governments will control computers if they're used for factoring or discrete log. So it will be a very highly controlled product. So IBM makes roadmaps. I'm not going to go through this. It's interesting. They make very detailed roadmaps, and every year they change them. It's very interesting. If you have nothing to do, you take all the roads in the last years and you look at them, how they've been changed. I talk to technical people in IBM, and they say, well, the marketing produced this. Okay. They make progress. They have cool stuff. They offer stuff for academics. But I would not waste my time studying this roadmap for hours and hours to really understand where they are. I like Google roadmap. Here's Google roadmap. Milestone 1, beyond classical. Milestone 2, quantum error correction. Milestone 3, building a long-lived qubit. Milestone 4, creating a logical gate. Milestone 5, scale up. Milestone 6, large error corrected quantum computer. This is the one which can break RSA and ECC. Where is Google? They're here. They were here 2 years ago. So they were the first ones to be able to correct a single bit. So, but these guys in 2001, they factored 15, but they couldn't correct a single bit. How could they do that? So in fact, all the computations announced on quantum computers are fake, because only 2 years ago, people were able to make a single bit and correct the errors for a very short time. Okay, as you can see here, error rate was 10 to the minus 2, and it was probably something like milliseconds or so, if not less. So this is what Google announced. That is when they announced Willow last October. So in fact, this is seen as the most powerful one that can really also do stuff that classical computers cannot do. I think that's now everybody agrees. So if you've been following the press over the last 25 years, you've seen factorization of 15, 21, 35, even RSA 2048. That's what they did there. They just chose P and Q very close to each other, and then they search for the difference. And if you have the difference, then you can factor. That's an exercise for a 15-year-old. But if you can put quantum in front, then you apparently can get the world press. It's very interesting. So some cryptographer got really upset with this, Peter Goodman, and he wrote a paper about replication of quantum factorization records with an 8-bit home computer, an abacus, and a dog. And so more or less, his point of view was that all these things, what they do is they predict the answer, and there is only a few possibilities, and then they keep trying until they have the right one. And it's not even exhaustive search, because they program some things in there. It turns out that one of my friends told me that, in fact, even the physicists wrote these papers already. So on arXiv, you find the paper pretending to factor a large number on a quantum computer. And then they published it in Nature, but Nature made them tone down the title because they found it too insulting, so that they called it oversimplifying quantum factoring. So you can, as a physicist, not insult other physicists. This is not done, okay? But so in fact, so now I'm making fun of this a bit, and so you may think this is not happening, but it's actually not true. There is just overselling. And if you look at the insiders, that's Scott Aronson and so on, they actually say we are making amazing progress. So I'm making a bit fun of things, but that should not think that it's not going to happen. Billions and billions are being invested. The stakes are now very high, and I think it would be very dumb to bet it will not happen. That would be my thing. So if you really want to know what's happening, you ask the Germans, with Deutsche Grundigkeit, they will give you the answer. So BSI has a very long and detailed report, the status of quantum computer development, in which they look at all the building blocks you need and all the technologies, so they compare them, and they have go from basic function to error correction. And so they look at all the technologies that are available and they rate them. So if you really want to understand what's happening, I would say read this report. And again, if you look at the last version from 2024, they say 16 years actually may be enough, and it may be even faster. So in spite of all the joking about dogs and abacuses, I think it's not smart to bet it's not going to happen. So Sam Jacques makes also this very nice plot. Again, it's a multi-dimensional plot. It should be probably 5 dimensions. But what he shows is the number of qubits in a log scale and the error rates. And so to factor RSA, you need to be here. To do quantum chemistry, so to invent new molecules, you need to be there. To do error correction, you need to be in the blue zone. And then this is the gray area. This is where we've been. So it has taken about 35 years, because you saw the first research was actually early 90s. So more or less 35 years to get into the gray zone. But then, of course, this is the 2024 graph. Then I told you there was a breakthrough by Google of a factor of 20 for the RSA number of qubits. So this is the graph of 2025. You see the RSA curve now has shifted to the left. It's still a very big gap. It's not going to happen tomorrow, but things are moving. The error correcting codes get better and so on. So we actually don't know what's going to happen. What you can do, Michele Mosca does this, you can ask experts in quantum computing how likely they think it will be that a quantum computer will factor RSA 2048 in 3 years, 5 years, 7 years, 10 years. And then you can plot this. And this has been happening in many years, and it keeps shifting a bit forward, but the probabilities are going up anyway. And so, again, you have to take this with a grain of salt. They're the experts, but also they get funding for this. And if you get funding, you're not going to say it's not going to happen in 20 years, right? It's like the same thing if you get funding for fusion, you're not going to say, oh no, fusion is never going to happen. And then you ask for 2 billion. You will always say to the politicians, it's going to happen in 15 years, right? And by the time you'll be retired as a manager, and then somebody else can explain why it takes another 15 years. I'm joking again, but I would not take these things as gospel, but at least I would actually take it more credible, make it more credible if there were their name attached to it. But this is just experts. I trust their experts. I trust Michele that he asks experts. But if it's anonymous, they also have an incentive to bias this data. But it's very useful information. And I haven't seen the more recent one, but I'm quite sure that the numbers have improved again. You can, of course, also be more cynical, like Adi Shamir, but of course, he is a bit biased because he's the S in RSA. And he created an algorithm at young age that after 10 or 15 years suddenly secured the whole world. And now he's retired, and now he sees that we're going to remove it. So he's probably a bit upset about this, disappointed. So he says, actually, it's not a real problem for the next 30 years. So he doesn't think that these things will be built. So there was a very nice paper also on arXiv last year showing what actually are all the risks and why it could go wrong and why it's not so sure we're going to work. But okay, it doesn't matter. So you make your number. Everybody makes their number. So when should you switch? So this is the only equation you get. It's known as Mosca's equation. So you guess how long it will take. Everybody makes their own number. Then you try to estimate how long it will take you to shift stuff. 3 years would be really fast. 12 years would be okay. But I told you that EMV, they have a time horizon of 15 to 20 years to change things. And then how long does that need to be confidential? Okay, so for business purposes, it's typically 10 years. And then Mosca's equation says you should switch in 2026 plus Q minus X minus Y. This is the only math I will show you today. Okay, you can all handle it. Okay, let's plug in some random numbers. Say Q is 14, so you think it's going to happen in 2035. You can change in 4 years, you're an optimist. And Y is 10, then you need to actually start changing today. And so this is the details of this. So I'll give you more details, but the standards have been published in 25. And so the first implementations are there. But I think where the bottleneck is now is that there is no certified implementations. So apparently FIPS 140 has a great, exciting backlog of libraries. You can't see what is in there, but the backlog, given who sends updates, it seems that it's probably all the big players have their libraries submitted to NIST, but they had things like shutdown and so on. And so it seems that they're behind, and that at least it will probably take till the end of this year before certified libraries are available. And for many businesses, this is important that it's certified. A few more observations on this. Of course, for signatures, you don't need to worry. If you have a code update mechanism and you update your mechanism in 2034, the day before this first computer comes on the market, you're still okay, right? Because then you resign your old code and your new code, and that's one thing. That's the good news. The bad news is that your medical data probably should be secure for 50 to 100 years because it has your DNA in there, but affects your kids and so on. So I would not send any medical data over TLS today because it will not be secure. If you're a government, what is your time horizon? Typically 50 years of classification, minimum for classified data. So they're actually in trouble because if they fill in Mosca's equation, and I think they're smart enough to do it, then they will find out that they have to migrate in 1994, which is before Shor's algorithm was invented. So this is now you understand why governments are so worried, because they're already way too late. There's also a very nice discussion happening on some news groups that says, well, people worry about this harvest now, decrypt later, but we send billions of connections every day with different keys and so on. There is no economics to decrypt all this. So average users should actually not worry about this, because I think that's one, there's no economics for this. I would say if you use ephemeral keys, then it's fine. Every time you use new public key, indeed, you break the economics. If you use like Diffie-Hellman with a fixed prime number, then it's not the case, or a fixed elliptic curve. Then there is a problem of economics. But still, of course, if you spend $1 billion on a computer that costs a lot of money to run, you're not going to use it to read the messages of Bart Preneel from 19. That I also understand, or any of you probably. But of course, the message of the prime ministers and the minister of defense and whatever, and all the classified communication. So so I think there is also a bit of overhyping of the problem. But I think that's also clear. So the people in physics, they're very good in their marketing. So they say, well, so what you now have today is lattice-based cryptography. But they say, oh, we have QKD, quantum key distribution. It was invented in 1985 by Bennett and Brassard. This is the first demo, 1989. And so they're now getting hundreds of millions of euros, if not billions, to build QKD systems. And I was in an interesting meeting in Brussels with the Commission in 2004. And then as an outcome of this meeting, they got 3 times more budget than the cryptographers got. And now it got completely out of hand. I think they have a budget of something like $500 million, if you count it all up. Fabiana says more, probably $1 billion, while post-quantum has a budget of tens of millions. If we're lucky, if we get 100 million. Now, QKD, I told the Commission in 2004, this is very cool, but it's not going to solve any real problem in the next 40 years. People in quantum physics said, no, we're going to solve everything. There was companies and startups and business plans, and they made all these curves, these hype curves. And I guess it's now a long time enough ago, I made a study for ENISA about the market potential of QKD in 2018 or 19. And I wrote in my report, the market potential for QKD is the research budget of governments spent on this. And ENISA shelved this report. It was put in a drawer and not published because it was kind of a bit, I guess it was not allowed for ENISA to criticize the European Commission at that time. Well, I guess it's never allowed for ENISA to do that. And so this report was never made public, but I was right. I should now actually get it out and say, look, this is the market for QKD, and this is the research budget, and it's actually exactly the same. But there is no commercial case for QKD. Okay, that's enough QKD bashing, but I think, am I upset about it? No, not in the sense that, well, these guys do cool research, and it's physics. They will invent new stuff. Maybe we'll have better whatever in the future. But I'm still quite shocked that you can have something that all scientists, well, the majority of scientists, except for a small set, agrees that this is complete nonsense. I mean, BSI made a report, ANSI made a report, the Swedish made a report, even the Secret Services wrote a joint report in Europe, which is unheard of, saying don't spend money on this. And the Commission just goes ahead, which I think is a problem for the Commission. If you want to actually see we're under threat, we have to get our defense together, we have to become more sovereign, and then you see that they can actually throw away $1 billion in a critical sector and ignoring all the facts and all the science. But okay, so PQC. So what happens in cryptography if you need a new algorithm? We do a competition like the Olympic Games for cryptographers. So after a long discussion, and I guess a bit too late, but okay, 2016, NIST published a call, and they got 86 algorithms. They asked for signatures and encryption, and people tried many things. What is the main lesson from this diagram is that you get, if you ask cryptographers, give us something that's secure for 50 years or more, then they will get you 82 algorithms. And after 3 years, about 60% of that is broken already. Okay, so don't trust cryptographers or be very careful with what they promise you and be prepared to change. Again, the other main lesson is that if you look here, what was kept, the last number, it's just only lapises. All the rest was actually broken except for hash-based signatures, which is something that existed in the 80s and it has been slightly optimized for the competition. No, I will explain that to you immediately. Because actually we submitted a lattice-based scheme at KU Leuven, and you know that we always win in this competition. We won the AES competition, we won the SHA-3 competition. And so we submitted a fantastic scheme called Saber for the lattice scheme, but NIST selected something else called Kyber. We think our scheme was better because it used a rounding rather than noise, so it would be much better for hardware. But NIST chose the wrong scheme. Then we were so upset that we actually broke COSIC. So this is the isogeny-based scheme. We actually broke it. And the researchers got a $50,000 award from Microsoft. NIST also kept another high potential algorithm, and White Berlins broke it on a laptop in a weekend. That's what you get. This was already after 4 years in the competition, some of the most trusted algorithms. So KU Leuven was a bit upset, and don't make KU Leuven upset, okay? Then we just break stuff on a weekend. Yes, in both cases, yes. Now, Wyatt has now been hired by IBM, and he broke another scheme, but he's still KU Leuven school. So more or less, IETF published 2 schemes, hash-based signatures, XMSS and LMS, which are actually really small improvements to 70 schemes that were actually known in the 70s, hash-based signatures. They're okay. The security is good, but you can use every key only once. And if you lose state, and then in fact you compromise your secret key. So it's really, we call this the cryptographic foot cannon. So if you misuse it, then you will lose all your security. So it is only for, it's not something I really like to see in standards, because I've been in this business now for 35 years, and I could probably talk to hours about all the things people do wrong in implementations. So putting out a standard that says like, it's good, but don't misuse it. Okay. So NIST selected in the end MLChem and MLDSA and then SLHDSA. They actually, and then a year later, they selected also HQC, Chem, and FNDSA. These standards were published. So what I don't like is that these schemes had kind of cool names like Kyber, Dilithium, Sphinx Plus, HQC, and Falcon. And NIST managed to make these names unpronounceable and unrememberable. Even I can't remember these names. Thank you, NIST. Okay, so now, if you understand these algorithms, you're seen by all the other people as a crazy person because you can remember 5-letter combinations that nobody else can. So more or less, Sphinx Plus is hash-based signature that is stateless. So you can actually lose your state. So MLChem and MLDSA, this is modular lattice signature and key encapsulation mechanism. This is code-based, and this is Falcon. This is a lattice-based signature scheme. The Germans and the French like FrodoChem, which is kind of a slower version with bigger keys of Kyber. And then the Germans like Michaelis, which is a scheme from the 80s, code-based, different mathematics. But the French hate it because somebody found a statistical deviation in something which cryptographers agree doesn't mean anything, but now the French think it's broken. And this is like it because the public keys are like 0.5 megabyte. But the ciphertexts are very small. And there is a new competition ongoing for signature schemes. You understand right away where. And of course, Korea has their own competition. China is starting a new competition. And Japan also wants to have their own standards. So the nice world of elliptic curve and RSA are over. You will have to deal with at least 10 or 12 algorithms, which each have at least 3 versions in terms of key sizes. It's going to be interesting. So the schemes actually, people always say this is slow. No, in fact, at this moment, the lattice-based schemes and the code-based schemes, they're faster than RSA and even ECC. Well, nobody can beat RSA with small exponents. So for verification or encryption, RSA beats everybody. But in fact, ECC and RSA are cubic in complexity and linear in key size. All the new schemes are quadratic in key size and complexity. So in fact, they're more efficient, but they have large keys. That's it's different math and different parameters. So as I said, nobody can beat RSA encryption, but like key agreement is 5 times faster than the fastest ECC. So speed is not a problem. And the encryption is even faster than RSA and ECC. But of course, key size and ciphertext are 3 to 15 times bigger. Same thing for signatures. Public key and signature is even worse, goes to 30 times bigger. Signing is faster and verification is comparable or faster. What we don't have extensively is standardized knowledge proofs, OPRFs, VPRFs, whatever, all these kind of cool primitives that have been deployed already. You don't know about this stuff, but it has been deployed. For many, we're still struggling to make post-quantum versions. So there is still an army of researchers, cryptographers working on all the problems, because this is just encryption and signatures, which of course is 99% of all applications. So here are some graphs that give you an idea of where we are. So this is public key size, and this is ciphertext size. And so as you see, elliptic curve is here. Less than 100 bytes for both. RSA is like 256 bytes or something like this, that order of magnitude. Here is Michaelis, 1/4 of a megabyte public key, but small ciphertext. And all the schemes we've standardized are more or less in this region. So this is a problem. It's a problem, yes, because as we'll see, it breaks some stuff. By the way, it's not the latest graphs. This is a bit old, 2019, but I don't think these things have changed substantially. It gives you. Here's another graph from signatures. What you have here is public key size and signature size. So here is EDDSA, public key 32 bytes, signature 64 bytes. Here is RSA. So the only scheme that can beat it is not standardized yet, is isogeny-based key sign, but it's very, very slow, what you can't see. It's like 50 to 100 times slower. So SLDSA, this is Sphinx Plus, has actually quite small signatures, but sorry, quite small public keys, but huge signatures. Signatures are like 40 kilobytes, which is okay for a code update. It's not okay for a transaction. And then, so now you understand, and then MLDSA, this is the default one, sits here. So this is both are bad, 2K signatures, 2K public keys. And then now Falcon, as you see, is actually smaller. This is why I standardized. Falcon is a nightmare because it uses floating point arithmetic. Floating point arithmetic is trouble. You can't implement it correctly and securely. So I don't know why they standardize it. To give you an idea, they actually agreed to standardize it, and then it took them a year to figure out how it really worked. This is why the standard was a year later. So after 4 years, they actually chose it, but didn't know how it worked, which to me is not a good sign. And it's a brilliant design, good designers, but I would never use it. But of course, you can see why people want to use it, because it's more compact signatures. It is, but it's going to be soon. The draft is out. But it was delayed by a year. And the name is already announced. FNDSA, the best name ever. FNDSA, who could have told this? Okay, so now you understand why there is a second competition. So there is, in second competition, there is more multivariate quadratic schemes, and there is a whole set of schemes here that actually give you small signatures, but kind of large public keys. And there is also some here, like Feast, multi-party computation in the head, that gives you small public keys, but larger signatures. But we really would like to have something here. And the only thing we have is key sign, isogeny-based, but then it's very, 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 very slow. So in fact, we still don't have a solution that is compatible with what we have. Here is a graphical presentation of this. But you get the slides, you can look at it later. I try to summarize. What I show here is the sum of public key and signature size. So I didn't show this separately, but the sum, and the sum is always bad. Why do I show this? If you have a certificate, you always have a public key and a signature. right? And as you see, the insecure things have greenish stuff, but all the rest has some problem somewhere. In either performance or like ski sign is terrible in performance, 177 times slower than MLDSA. Okay, so you always have something red. So this is more or less a summary. The most robust schemes have worse performance. By the way, if I show performance numbers in this graph, this is for 3 security levels. So there is 3 security levels, 128-bit, 192, 256. So this graph shows you the 3, right? But if people quote performance numbers, they always give the low security level only, because it becomes even worse. So I guess you're not surprised by this, right? So what people announce is security of the big ones and the performance of the slow ones. That's what you get on the label. So we're stuck with lattice-based schemes, more or less. A good performance. So if you don't trust the structure in these model lattices, you can use photochem, but then your keys are even bigger. And there is kind of some problems. For example, these things may have decryption failures. Falcon has this floating point stuff. You have to sample noise because they didn't choose rounding as we proposed. It shows you have to add noise, which is kind of tricky to generate the right noise. If you better random generate it, then your key will leak. So it's actually the same thing as elliptic curve DSA. If you make a mistake in your noise, in your random numbers, then your key is compromised. It's not something as a cryptographer you like to have in a scheme. And then there is, of course, side channel resistance. In fact, it was surprising how little work was done on this in the competition. So now the competition is over, and now people, if you now go to chess, you will see lots of papers studying how to make it secure against fault attacks, against side channel attacks, power attacks, and combined attacks. This is still a research topic for the next years. Okay, so we're now in the pre-quantum era. Everybody except for the NSA will go to the hybrid era, where we combine both schemes together, because we actually don't trust MLChem that much. So we still want to keep using ECDSA because we have no proof that there is no quantum algorithm for lattice problems. So maybe it could be, in fact, and in last April, there was an announcement which turned out to be wrong, but it could still be that a brilliant person finds a lattice algorithm, and then we have a big problem. So you better keep both. And then, of course, at some stage, we will, if the computers are there, we will stop using RSA and ECC. So now what you can do for signing, you can sign, of course, and check either one of them, which is okay. You put 2 signatures, and the recipient decides which they check. Or you can require that they should check both, and then you're long-term secure. There, the problem is easy. For encryption, of course, if you do an OR and you encrypt the session key with RSA or ECC and separately with MLChem, well, then you will not be secure for the future, because if I collect your stuff, I can decrypt it later based on the RSA or ECC decryption. So you have to do the AND, which means that both parties have to implement both algorithms. So this makes your migration more complex because everybody has to be migrated. And as I said, I'm very happy to have open source team here. So we have to update 60 billion devices, applications, libraries, whatever, 60 billion. The cryptography problem is solved. Well, the signatures would be great to get the real signatures, the same parameters, but I don't think this is going to happen. So we have what we have, but now get this in 60 billion devices. So encryption turns out to be easier because you don't need to upgrade AES. By the way, if you then decide to upgrade to AES-56, then you also have to use the high security level version of your public key stuff, and then you're 2 times slower and 2 times bigger. So you have to be realistic, right? It doesn't make sense to use AES-56 with the low security, 128-bit security of your key exchange scheme. So that's what everybody seems to forget, that the cost is not 40% more for AES. The cost is a factor 2 in performance and in overhead. For signatures, there is a very big problem because we can't agree. For example, do you hash the message before you start signing, or do you hash during the signing? This is like the ECDSA versus some other variants of schemes. Then the private key. So you can have a short private key because what you do is you generate, it's a seed, and from this you generate your private key every time you need it. Now the private key, should it store the seed or should it store the key, or both? Well, nobody can agree depending on your application and your business. If what you want to sell more, you will try to have the standard do either of them, but of course you have to have a standard before you can actually agree. So I didn't go to these meetings, but it must have been fascinating. So in IETF, there were 26 variants proposed for signature formats and key formats. 26. And then they argued for a very long time, and they ended up with 18 variants. And then they argued even more, and now they recommend only 6 variants. What can go wrong? This is not cryptographers. This is business people and maybe some stubborn implementers who don't want to give in and keep shouting more in the IETF. But like, how difficult can it be to agree on a format for signatures and keys? Apparently, it's very difficult. So signatures code updates is the very important application. This can be done. Code signature size doesn't matter. We have good schemes. Use Sphinx Plus, and you're done. So I'll come back to TLS Handshake, but you should understand that Handshake has 5 signatures and 3 public keys. So instead of, if you use ECDSA, this is a few hundred bytes, or RSA, it's a bit more, but still less than a kilobyte. It suddenly becomes 7 to 9 kilobytes. And don't forget that the MTUs, in fact, what fit in one packet no longer fits in one packet. And so there is also a lot of TLS rollout. There is 15 billion devices, a lot of ossification. So people implement things hard-coded. There is all these TLS middle boxes invented by the banks to intercept communication of employees and so on, and also by governments to intercept stuff. So all this stuff will start breaking. So this is a very big problem. So more or less, also PKI. So you get certificates. You have to sign the old key, the new key. You have to sign with an old algorithm, a new algorithm. So there is 4 signatures. Every signature has 18 possible formats. The fun is going to start. You thought X509 was complicated. So they're still looking at this. And then for HSMs, just shout at your vendor. I guess the HSM vendors will probably have already now ML, whatever, but they probably not have it certified. And that's going to be your problem. Yes.
Signatures themselves, the X509 formats. I think NIST gives you 5 different choices. Is the market standardizing on it?
I don't know. I mean, you have to ask the market. I do think the cloud vendors and so on, they probably agree. So, but then there is all the other players, right? There is, if you look at the ecosystem, there is all this divided ecosystem. So, it's the Bluetooth ecosystem, the this ecosystem, that ecosystem. Yes. So I will not explain it in detail because I don't have time, but so more or less the people in IETF, they realized that it's not going to work for TLS. So TLS, as we will see, it's already, there is quite some rollout, but the 7 to 9 kilobyte is not going to work. Okay. Then you may also have seen that lifetimes of certificates, when TLS was rolled out, people did just 30 years and then 10 years. But if you have a lifetime of 10 years, it means that the person who installed certificate is retired or is in a different job and nobody knows what to do. And then your website breaks and the CEO shouts. So they now go to, they follow more or less, let's say, encrypt approach, which is 3 months certificates. And then you can, in fact, ignore revocation, or revocation becomes less of an issue. Let's say encrypt doesn't do it. But also, because of government attacks, we have certificate transparency, where you want to log every certificate in the database, so you can check, is this a public certificate or not? The service is operated, for example, by Google, but also by Cloudflare. This is a free service for all of us to make us more secure and to stop some government attacks. But the problem is, if you issue more certificates, then this CT starts breaking. And also the certificates become bigger, so it's all a problem. So some people got their heads together, some bright people, and they realized it would be better to do the opposite. And first log your certificate. The CA makes a tree with certificates. And then only when this tree has a certain size, then you start distributing it. That's more or less the idea. So instead of first making certificates and then putting them in a Merkle tree, you first make a local Merkle tree and then you merge it into a bigger Merkle tree. And this has many benefits because it means the certificate is now a signature, a public key, and an inclusion proof that it's in the Merkle tree. But if the recipient already has been to the website or got preloaded some extra data, namely the signature on the root of the Merkle tree, a certificate only is an inclusion proof, which is a logarithmic number of hash value. And so, in fact, what they found out is that if they roll this out, at least if you have the root of the Merkle tree signed already cached, in fact, it speeds up TLS, which I think is really cool. Of course, we'll have to see whether it's going to work and whether there will be new attacks on this stuff and so on, because well, it can give new DDoS attacks and so on. But I think it's very cool that kind of the need has pressed people. There is it's still not standardized. There's a draft in the IETF. Of course, the stakes are very high because these CA companies have very big vested interests, and changing the infrastructure will be very expensive. But there is some very nice work being done there. Okay, then finally, So I guess software developers know PQC is not a cryptographic problem anymore. It's a software migration problem. Okay. But it's a very difficult one. It's the biggest one we've ever seen. The next big one will be the Linux 2038, right? That's the next thing. But we can now focus on this one for the next 10 years. And then, if you want to do this, you go to your boss and you say, our customers want PQC. Good, says the boss. And what is the revenue? 0. Because the customers will not pay extra. They just say, we want to be secure, implement a new standard. So this is very challenging. I've seen many companies where there is a lot of shouting happening because more or less you have to make a big migration. It costs a lot of effort, developers, testing, integration, new versions of product, and the customers are not willing to pay a cent for it. So it's very big tension. So the advice was to people, make a crypto inventory. So, and people even try to sell tools for this. It turns out that most vulnerability tools can do this already for you. You don't need special tools for this. But I think most banks will find out that between 5,000 and 20,000 applications using public key cryptography for a large bank. So what will you do? So what you should do is really, what is the risk? What are the risks I face? And what can I migrate quickly, make quick wins, and then see what you do with the rest? And probably the decision may be in 5 years to shut down some applications. So the idea of first look at everything. Also, there's a supply chain thing. Maybe you say, oh, we decided HSM is important, but your vendor says, are we only going to migrate a certified? I can only give you a certified version 2028. And if there's no more shutdowns in the US, if there's more shutdowns, it will be 2029. That's the reality on the ground, right? I mean, as an academic, I can say, oh, you migrate. But in business, of course, you have supply chain to deal with, you have certification to deal with, and so on. This is what makes it very hard. So it's a 10-year agenda. And you can also say, should I maybe take the risk? Maybe I listen to Adi Shamir and I will not do this. Well, I think it's too late. The governments have decided this to happen. And so, as we will see, the regulators will impose it, NIS2 will impose it, CRA will impose it, and so you will have no choice. Well, is it needed? Maybe Shamir is right, but it doesn't matter anymore what Shamir thinks. What matters is that if you don't upgrade, you will be in trouble. Okay? So what is easy? Messaging, network security, except for the PKI, of course. What is difficult? Secure boot and update signatures. Why? Because these devices are not so easy to update, right? You have to change all these things which are sitting there in all these IoT devices. There is now 21 billion IoT devices, and they're kind of embedded stuff, embedded engineering. It's not just put a new version on there. I mean, very often public keys are burned with fuses. And okay, 64-byte fuses, that's okay. But you know, if you suddenly say, now I need 3 kilobytes of fuses, somebody will shout at you. PKI is a disaster. Also, all the middle boxes that break TLS, the interception of this. So they actually don't follow the standards. This was already a problem in migrating to TLS 1.3, that the standard was ready. And then it turns out that you couldn't roll it out because if you did this, then because of all kind of ossification and middle boxes, the things broke. And then, of course, your customers shout at you. And platforms will be very hard. I mean, if you like a big platform, Amazon, Microsoft, Google, of course, they have a very good control over it. But of course, they have thousands of services, hundreds of products. And for them, this is a nightmare. Of course, what we all say as cryptographers is, oh, but in the future, changing algorithm should be easy. That's nice to say as an academic. In practice, I think most people are already with the water here, and they're not going to do this. They're just going to put in MLChem and hope it will be good for the next 10 years. But of course, ideally, you should now learn this lesson and make sure that next time when MLChem is broken and you have to implement Macalis, you actually will be easier. But I'm kind of skeptical that this is going to work. It's a buzzword. Browsers is good progress. As you see here, you see how Chrome, Android, OpenSSL, probably also some open source libraries. There is a boring SSL I know is, I talked to Google recently, they're in the FIPS pipeline. And I guess some other open source projects, you'll hear more about this. They probably have done their work. Sigma is upgraded, for example. So there is quite some deployments. This is Cloudflare blogging about this. So Cloudflare also now reports that 63% of all global traffic is post-quantum. The traffic they see, which is, of course, a very selected part of the internet. This is the services that need high bandwidth, so many users. And Belgium is 68.7, so we do better even. to give you an idea, there is 18 million TLS connections per second in Cloudflare about performance issues. 38% of the top 100K web servers has migrated. But if you look at the origins, the smaller things, it's only 3.7% has upgraded. So in fact, the 68% may give you the impression that, oh, we're well on track, but in fact, we're only 1 in 30 has upgraded, and 29 in 30 have not upgraded. Yes. So what about migration? So the NSA, of course, they have done illegal things in the past, so like many other governments, so they actually don't think 50 years of security is enough. So already in 2016 or 15, they said stop using ECC or don't buy new ECC hardware. And then they made a recommendation 4 years ago, which is interesting. If you look at it, no AES 128. So they have not read some Jacques papers, or I guess they want 50 or 100 years security. There is no Falcon in here, and there is only level 5 in here. So no level 1 or 3. So if you want to sell to the US government defense, you have to have level 5, and that's all they want. And they have a migration path where everything should be done by 2032. That's 6 years from now. Good luck. And some stuff should be done 4 years from now, software signing, networking. And they have no hybrid. And nobody understands why. So they just say dump ECC and RSA. So there is kind of these arguments that maybe they think hybrid is too complex. There will be too many bugs in the implementation. Or maybe they can break ECC and RSA for breakfast with a classical algorithm. And they think it's like, don't spend time on it anymore. Or maybe they just want to create confusion in the market and make sure that all vendors have to have a version for NSA and a version for the rest of the world. We don't know. And nobody understands why they don't want hybrid. But given they protect US government secrets, it's kind of an indication they must trust MLChem because, they seem to be sure it's not going to be broken. NIST made a timeline, November 24. They more or less said, if you have low security level, you should upgrade by 5 in 5 years. If you have the higher security levels, RSA 2072 and so on, you should upgrade by 2035. And that's when you should be ready. This is what NIST did. The White House, one of the last executive orders of Biden said, secure BGP and DNS, encrypt your email, use end-to-end encryption, use TLS, and include PQC as soon as practical. Okay, very high urgency from the Biden administration. The fact that the Chinese were discovered in all the telco networks of the US, also the same order recommended to stop using phone calls for any government business and switch to WhatsApp or Signal or whatever, which they did, as you know. The Hexet committee on Signal, he did what it was to. It was still not good enough, but okay. It's not for the classified stuff, right? Then Trump, in fact, he was not high on his list. It was only in June that he responded, and he said that there should be a list of products. TLS 1.3 will be mandatory, but he removed PQC support in project solicitation, so in the call for tenders, and he also removed international collaboration, which is not so surprising, I guess. Canada, actually, because of the Waterloo team, they're very much ahead. So Waterloo has a big investment, Michael Mosca, but also others in cryptography, and then also in quantum. And so they've also in QKD, but also in quantum computing. So they actually made roadmaps, and so they're actually pretty much ahead. Some of these documents are already in their fifth version. They already exist for 6 or 7 years. So they're interesting stuff to look at. The EU in April 24, so this is 2 years ago, they said, need to make a plan to have a plan. That's what it is. That's my summary of it. And then the member states said after 6 months, yes, we should do something. But of course, it's completely hypocrisy. And of course, also the EU-funded PQCSA, this project that makes this workshop possible. Thank you, Fabiana. And also Picasso, there is another project. So they funded research. In fact, I should also say good things about the EU. For example, a lot of researchers submitting in the NIST competition were funded by EU projects. And in fact, if you look at many of the algorithms had EU designers, and most of the research was done in Europe. But the bad thing is that most member states don't want the EU to deal with cryptography. Article 4 Treaty of Lisbon says national security is our business. So the EU cannot even produce a list of recommended cryptographic algorithms. And I produced one with the eCrypt project for a long time, which was widely used by industry. Then ENISA was so kind to take it over. Then ENISA was told to unpublish it. And then ENISA actually was told to stop producing it. Okay, so surprisingly, in fact, Europe has a list for the electronic signature directive, which was under control of ETSI, and then it came under control of SOGIS. And so SOGIS, the senior official group for information security experts, they were created in '91 for the ITSEC. I've never been senior enough to be there. I'm always too young to be in the SOGIS group. No, I'm just kidding. This is, of course, always SOGIS is only government officials. I'm not a government official, luckily. But so they produced a list, which is more or less, in summary, what France and Germany and a few other countries can agree on that is good for common criteria. So it's a very, very small list of algorithms where France and Germany agree, and it's for common criteria. So it's a very narrow publication. And so this is what they agree on. And amazingly, FrodoChem and MLChem are in there. But then last April, they said, for new products, at the end of this year, you can no longer come with IRC 2048. A signing application. This is complete nuts, okay? It's kind of, everybody falls from their chair. The industry is very upset. But of course, if you're in the common criteria business, you don't charge it to government because the government is your main customer. So nobody says something, I will say something. This is nuts, okay? And you can all agree with this. This is nuts. And then, of course, people criticize NIST, and NIST has the NSA as a back channel, but at least NIST publishes calls. NIST asks for your comments. They may ignore your comments, but at least they ask for comments, and they make a new version, and they say what you did with your comments. In Europe, it's a secret body of older people meeting in a back room from some member states and making decisions for all of us. Academia, not necessary. Industry, not necessary. Open source community, not necessary. I think they still live in the 20th century. What can they agree on? Common criteria, that's all. And also a lot of effort being spent in Europe on to agree what you can export to bad countries. So we can also agree what is bad crypto. There is every 2 years, they update the regulation of dual use, and you find all the bad crypto in there. We can also agree on that. What is bad, we can agree on. What is super secure, we can all agree on. In their section, we can agree, but what everybody should use as a normal person, as a bank, as a telco, we can't agree, we can't make it public. There is, of course, a French list. There is a German list, there is a Dutch list, there's probably several German lists. There is also a classified French list for government security. And this is what Europe does in cryptography, which of course is terrible for all the small member states and is terrible for the common market. You can't go on the square in Brussels and shout common market and then just even refuse to publish a list of algorithms for cryptography that I recommend. But okay, now there is also this cooperation group. So this is a critical infrastructure. And they also recommend to go to, they published also a report, all happened last year. So after, I would say, 10 years of inactivity in Europe and passivity, last year was very active. Since November 24, things started warming up. And so now they said for high risk, you have to do something, you have to be done by 2030, for medium risk, 2035, and for low risk, well, whatever. So at least there is some recommendation if you don't want to get a problem. But of course, you may have seen that, or you may understand that NIS is, again, it's a directive. So every member state keeps their own autonomy. And I think it's still, NIS should have been, of course, a regulation which have applied to everybody in the same way, especially for multinationals, this is a nightmare. And then you complain that there is no large European players, but you make these kind of critical regulations different in every country. And of course, now the member states have the authority over NIS, so they're going to fight now any harmonization, which is in the new CSA directive, more harmonization. I'm quite sure the member states will try to fight this. So I'm thinking about this list of cryptographic algorithms. Maybe I should just spend a few weekends and get a few hundreds of my friends together. We should just make a list again and just publish it just to annoy all of them. Just all agree on a list with a few hundreds of experts and make it public. Just to, just because it's for the common good and just because we can. Maybe that's the best thing to do. Okay, then the G7 even got involved. So now you can really see its top level, right? I mean, it's now Chef Sache, right? Post-quantum cryptography. I mean, who would have thought 10 years ago that the G7 would have a cyber group recommending things? It's for the financial sector, they make a migration plan. And so as you know, financial sector is regulated. So BaFin immediately said, this is what you have to do. Which means all the German banks wake up and shout all their vendors, this is what you have to do. So this is going to drive the whole industry. because the German banks and the French banks, and I guess the Belgian banks also a bit will shout at their vendors. So government, as I said, they should have started in 1994, so they're actually in big trouble with all the classified data. Health care, they have a very big problem because they have no budgets and they're dealing with ransomware. PQC is a problem for 2035. That's not their problem, although they actually have the most sensitive long-term data. Finance, as I said, driven by regulators. So the Singapore regulation, regulator already put some documents out. They even also push people to QKD. Let's keep a minute of silence for the people in Singapore who have to implement QKD to solve real world problems. But the Israel regulator is there, the Bank of England, ECB, BaFin, as I mentioned. Automotive, they're also interested because if you design a car today, it takes several years. Apparently in China it goes faster, but at least in Europe it still takes 3 to 4 years to design a car, and then this car will be on the road hopefully for 20 years. So they actually have a problem with especially code updates. I don't think they care about confidentiality of your data so much. They may pretend they do, but they really care about the integrity of the engine and you being able to change the security systems of the car or the engine systems of the car. And so they're actually looking at this as well. Most other sectors will not do anything unless they're pushed by the government. Okay, time to wrap up. So in fact, we don't know for sure whether a large quantum computer will ever be built that will break RSA and ECC, which is very interesting. So some people still think it's not going to happen. But there seems to be a consensus we can't take the risk. And the governments have taken this decision. And for them especially, because if you've done illegal things and you want long-term security because you don't want to go to jail, right? So they have a high incentive, of course, also for national security. Indeed, if your secret plans leak out, then you have a problem, especially in the current political climate. This has been more acute than I would say it was maybe 10 years ago. So everybody has to move. It has to be risk-based. You really have to look where your risks are. In an ideal world, you stop hard coding crypto and you look at crypto agility, but I think it's kind of a dream. And maybe the people at the bottom, the supply chain, the libraries can make it easier, but it's still going to be very, very hard to do this. And I guess we need an EU level strategy. And so there is now some strategy, but for example, there is no clear recommendation on, for example, which algorithms to use, and do we have other algorithms or not, and for which security levels and so on. There is no clear guidance at EU level. Quantum computers are not only scary, they also bring cool applications. But I guess it may still take a while. I will be probably retired, but it will still be big fun. Thank you very much for your attention.